So we're diving into something pretty massive today, something that'll really make you think twice next time you look up at the night sky. We're talking about missing matter, this mind-boggling concept that a huge chunk of the universe is basically, well, missing.
Yeah, it's a real head-scratcher. It's like we've done the cosmic inventory, counted up all the stars and galaxies we can see, and the numbers just don't add up.
Right. It's like trying to bake a cake and realizing you're missing half the ingredients. But here's the thing. Recently, a faint signal, something like a whisper from billions of years ago, might be offering a clue.
We're talking about a fast radio burst, or FRB for short.
And not just any FRB, right? This one's called FRB 2020-0610AA, and it's pretty special.
It is. This signal traveled for 8 billion years to reach us. Think about that for a moment. 8 billion years. This signal was emitted when the universe was still in its infancy. We're essentially getting a glimpse into a time when galaxies were just beginning to form.
Wow, that's just mind-blowing. So before we get into what this signal might be telling us, let's back up a bit. What exactly are these FRBs? They sound kind of like, I don't know, cosmic paparazzi flashes.
They do, don't they? They're incredibly intense bursts of energy, but they last just a fraction of a second, just a few milliseconds. We're still trying to figure out exactly what causes them, but some theories suggest they originate from these incredibly dense, highly magnetized neutron stars called magnetars.
Magnetars, okay. So these signals, they can actually help us find this missing matter. How does that work? It seems like a bit of a leap.
Well, imagine you're shining a flashlight through a thick fog. You might not see the fog directly, but you see how the light is scattered and dimmed.
Right, you can kind of make out the shape of the fog because of how it interacts with the light.
Exactly. Similarly, when FRBs travel through space, they interact with matter, even this invisible missing matter, and that changes their signal.
So by studying how the signal changes, we can actually map this invisible stuff between galaxies. That's brilliant.
Precisely. And there's a method called the Macquart Relation, developed by the late astronomer Jean-Pierre Macquart, that lets us use FRBs as a kind of measuring stick to estimate the amount of matter the signal has passed through on its way to Earth.
Okay, let's unpack this Macquart relation a bit. How does it actually work? We're talking about a signal traveling across vast distances in billions of years. How can we use that to, I don't know, weigh the universe?
Well, it's all about how the signal gets dispersed. When a burst of radio waves travels through space, it gets spread out. The different frequencies that make up the signal arrive at slightly different times, with lower frequencies lagging behind the higher ones. Think of a runner on a track. If the track is more crowded, it's going to slow them down.
So the more matter the signal passes through, the more spread out it gets.
Exactly. And that's the key to the Macquart relation. It links this amount of dispersion, how spread out the signal is when it gets to us, directly to the amount of matter the signal encountered during its long journey.
That's incredible. So we're basically using the FRB signal itself as a measuring stick. That's really clever. And the fact that FRB 2020-0610A, coming from so far away, supports this relation is huge.
It really is significant. It really strengthens the case for this missing matter and helps us narrow down just how much of it might be out there.
This is where it gets even more interesting, right? Because we know the matter's missing, but we don't know what it is. So we've got this missing matter out there. But what actually is it? I mean, is it just more stars and galaxies that we haven't spotted yet? Or could it be something much weirder?
Well, it's unlikely to be just more stars and galaxies simply because they'd emit light that we could detect, even if they're incredibly faint and far away. We've got other ways to look for that kind of normal matter, and it doesn't seem to account for the amount we're missing. No, this is something else entirely.
Okay, so if it's not the stuff we're familiar with, what are the leading contenders? Give us the rundown.
Well, one possibility is that this missing matter is something we call baryonic matter. This is basically the same kind of stuff that we're made of: protons, neutrons, electrons.
So the stuff we understand just hiding in a form we haven't been able to detect yet.
Exactly. For example, it could be in the form of vast, diffuse clouds of gas, mostly hydrogen and helium, spread out thinly across the vast distances between galaxies. This gas is incredibly difficult to detect directly because it's so spread out and doesn't emit much light.
Right. It's like trying to find a single grain of sand on a beach. So how do we even know where to start looking?
Well, that's where these FRBs come in. They can act like cosmic X-rays, allowing us to see this otherwise invisible matter. Remember how we were talking about how FRBs get dispersed as they travel through space?
Yeah, like the runner on a crowded track.
Right. So by analyzing exactly how much an FRB signal has been dispersed, we can get a sense of how much of this diffuse gas it's passed through on its journey.
Okay, so that's one possibility, regular matter just hiding in a really diffuse form. But what about the more exotic stuff? What about dark matter? Is that still a contender?
Oh, absolutely. Dark matter is still a major player in the missing matter mystery. The thing is, dark matter doesn't interact with light at all, making it completely invisible to our telescopes.
So how do we even know it exists? It's like chasing a ghost.
We infer its existence through its gravity. We see the effects of this gravity on the things we can see, like how galaxies rotate. Galaxies are spinning. But based on the amount of visible matter we observe, they're spinning much faster than they should be. It's as if something massive, something we can't see, is holding them together.
That is pretty wild when you think about it. So it's like trying to understand a shadow puppet show. We see the shadows dancing on the wall, but we can't see the puppeteer behind the scenes.
A great analogy. And when we add up all the effects of this invisible gravity throughout the universe, it seems that this dark matter outweighs the stuff we can see by about 5 to 1. That's
Yeah.
huge.
Wow, 5 to 1. That's a lot of missing stuff. So we've got regular matter hiding in plain sight and the possibility of this invisible dark matter lurking in the shadows. How do we even begin to figure out which one is the bigger culprit? Can studying these FRBs really help us distinguish between these possibilities?
That's the million-dollar question, and it all comes down to those subtle fingerprints that different kinds of matter leave on the FRB signal.
You're going to have to elaborate on that because I'm not sure I follow.
Of course. So imagine two FRB signals, one that's traveled through a region with a lot of diffuse gas, and one that's traveled through a region dominated by dark matter. Even though both signals will show signs of dispersion, the way that dispersion looks, its specific fingerprint, will be subtly different depending on what kind of matter caused it.
So it's not just about detecting the distortion, but the actual characteristics of the distortion tell us something about the culprit.
Precisely. It's like how detectives use fingerprints to identify individuals. Each type of matter leaves its own unique fingerprint on the FRB signal. And the more FRBs we can observe, especially from different directions and distances, the more data points we have to analyze and the clearer these fingerprints will become.
It's like having a larger sample size gives you more confidence in your results. So the more FRBs we can observe, the closer we get to solving this cosmic mystery. And that's where the next generation of radio telescopes comes in, right? Telescopes like the Square Kilometre Array, or SKA.
Absolutely. The SKA is going to be a game changer. I mean, we're talking about the world's largest radio telescope.
We touched on this a bit earlier, but for those who missed it, can you remind us what makes the SKA so special?
The SKA is absolutely massive. Its collecting area will be equivalent to a square kilometer. With that kind of power, it's going to be able to detect some of the faintest radio signals ever picked up from Earth, including FRBs from the most distant corners of the universe.
And so we're talking about potentially detecting thousands or maybe even millions of FRBs every year. That's incredible.
It's entirely possible. And with that much data, we're not just talking about studying individual FRBs anymore. We're talking about creating a three-dimensional map of the universe's structure, a map that charts the distribution of all matter, visible and invisible, on a scale we've never seen before.
Wow, a 3D map of the universe. It's like having a cosmic treasure map. But instead of X marking the spot for buried gold, we're talking about the hidden secrets of the universe itself.
I like that. And with each new FRB we detect and analyze, we get one step closer to understanding what this missing matter truly is and how it's shaped the universe as we know it.
It really is amazing when you think about the sheer scale of it all. These tiny signals traveling for billions of years, carrying secrets about the universe with them. It makes you wonder, with all this talk of dark matter and diffuse gas clouds, is there anything else out there? Could there be even more exotic forms of matter we haven't even thought of yet?
That's the great unknown, isn't it?
Yeah.
It's what makes studying the universe so captivating. We're always open to being surprised. While our current theories give us a good framework, there's always that possibility of discovering something completely unexpected, something we haven't even begun to imagine.
The unknown unknowns. Right, I like that. It's a good reminder that we're still just scratching the surface of understanding the cosmos. So, speaking of the unknown, are there other big questions you're hoping these new telescopes will help answer?
Oh, absolutely. Besides nailing down the mystery of this missing matter, there's that other big one, dark energy, that mysterious force that's driving the accelerated expansion of the universe.
Yeah, we touched on dark energy a bit earlier. It's like the universe is hitting the gas pedal, and we have no idea what's pushing it.
It's a great analogy. And, just like with missing matter, FRBs could be a key to unlocking some of the secrets of dark energy. These signals, traveling over such vast cosmic distances, their interaction with dark energy should leave some kind of trace, some imprint that we can hopefully detect.
So we can use these cosmic fingerprints, these subtle changes in the FRB signal, to understand how dark energy has shaped the universe over billions of years.
Exactly. It's like using the universe itself as a giant laboratory, with FRBs acting as our messengers, bringing us information from across unimaginable stretches of space and time.
Data that could potentially turn our understanding of physics on its head. It's both exciting and kind of humbling.
It really is.
Yeah.
With each new discovery, we realize how much more there is to learn. It just goes to show you the incredible scale of the universe and our place in it.
It's definitely a humbling experience. Well, unfortunately, that's all we have time for in today's deep dive. It's been an amazing journey, to say the least. But before we go, I always like to leave our listeners with something to ponder. Do you have a final thought?
I do. The next time you look up at the night sky, all those stars, remember that we're only seeing a tiny fraction of what's actually out there. There's a whole universe out there hidden from our view, full of mysteries and wonder. So keep asking those big questions, never stop exploring, and never lose your sense of awe and curiosity about the universe and our place in it.
I love that. Curiosity is what drives us to keep exploring and pushing the boundaries of what we know. A huge thank you to you for joining me on this incredible journey to the depths of the universe.
It was a pleasure being here. Thanks for having me.
And to all our listeners out there, thank you for joining us on this deep dive into the mysteries of the cosmos. We hope you enjoyed the journey as much as we did. Until next time.